we are going to analyze this DC-DC converter, this step-down converter, but in this case with an output LC filter. So we saw in last class basically this converter without the filter. So it was this situation here. So we have a transistor, okay, a diode, and a given load. In this case, between the transistor, the diode, and the load, we have a filter. And as I think I explained in last class, the goal of the filter is to eliminate the variation that exists in the output if the filter does not exist. Okay, so in situations where we want the output to be exactly constant in order to have a power supply for some electronic system that we have as a load. So it is in these kind of situations that we must use this filter that filters high frequency components and let pass to the output only the zero frequency, and the zero frequency is equivalent to the DC component. So that's why we get an output voltage constant in the sense that it passes from the source to the output, the DC component, and all other frequencies are eliminated by the filter. Okay. We are going to make the analysis of this converter, and also to see how can we choose correct values for the inductor and for the capacitor in order to get a desired behavior. But we are not going to make this analysis in the context of a filter. We are going to see this in another way that I will explain. Okay, but in this converter, of course, that we must well, in terms of the power that we have at the source and the power that we want at the output. And a function of the currents and voltages that are present in the converter, obviously we must choose an adequate transistor and an adequate diode, okay, that supports those currents and those voltages. Okay, but besides that, we must choose also an adequate inductor and an adequate capacitor. Okay, and we are going to see how can we do that. Before that, remember that in terms of control, okay, what do we control in this converter? This transistor. Okay, so it is assumed that we are using here a pulse width modulation control that we analyzed last class. Okay, so we are going to see if this is a MOSFET with our three terminals, so the gate, the drain, and the source. Okay, we control this transistor applying a gate source voltage. Okay, anticipating because we are going to remember this, and we need to remember this. We can control if this transistor is on or off, okay, by setting gate to source voltage greater than the threshold voltage that the manufacturer indicates in the datasheet. Okay, so if this voltage is higher than this one, we can put the device on, otherwise it is off. Okay. So we must apply here a control signal between the gate and the source. Okay, and this is that signal is the pulse width modulation signal, the one that we define is T on. Okay, and according to the period, we are defining the duty cycle. Okay, and so it is this kind of signals that we apply to MOSFETs and other transistors that we are going to see. So the control is this one. Okay, and since we have only a transistor, it means that we have only two states in terms of the converter. A given state between 0 and T-on, where the transistor is conducting, okay, and another stage of operation between T-on and till the end of the period, where the transistor is not conducting, so it is equivalent to have here an open circuit. Okay, we are going to analyze these voltage waveforms and current waveforms. Okay, in terms of the temporal axis, we have the period here at this instant, okay, and this other instant where we have this transition is I have here represented as dt, but dt is T-on, okay, so according to this formula that I recall, d times t is T-on. Okay, so in these figures we have here the first stage of operation between 0 and dt, and the second one between dt and t. Okay, so starting from the analyzing here these voltage and then the currents. Okay, what voltage do we have? The output voltage, but we are assuming that the output voltage is practically constant. Okay, and that's the idea, that's the goal of this converter. So we are assuming that we are able to do that, and the value, this value, of course, that there is always some ripple, some variation, but if the capacitor is correctly chosen, okay, then this variation is so small that we can neglect. Okay, so that's why here we are assuming that the voltage is constant. Okay, and this constant is equal to the average value of the output voltage. Okay, but how can I define this average value? Well, the relationship is the same that we saw in the last class. Without the filter, the relationship is exactly the same. Okay, so output voltage is equal to duty cycle times input voltage. Okay, so if I have an input voltage of 20 volt and I want 5 at the output, okay, I choose a duty cycle. In this case, D equals to 1/4, okay, and I get my output. Okay, so output voltage is constant. What do we have more? Inductor voltage, VL, is voltage across the inductor. And we also have here as an auxiliary variable this voltage V asterisk, that it is this voltage here. Okay, this node, assuming that the ground is down here. Okay, so basically V asterisks is this voltage, so it is the symmetrical of the voltage diode. Okay, and if we start from there, if transistor is conducting, okay, what is the value of this voltage? It is the input voltage. Okay. So in the first stage of operation, this red waveform is equal to VI. Okay. And in the second stage, so in this next slide, transistor is open. Okay. What is the value of this voltage? Well, it is 0 because now the diode is conducting. We have here, recall that we have here an inductor. Also, we have a capacitor, so two elements that can absorb and release energy. Okay, so at the instant when this transistor stops to conduct, okay, current that comes from the load and also capacitor, okay, forces the diode to begin the conduction. Okay, and so current flows in these two loops that are represented here in blue. Okay, current comes from the load, diode, inductor, but in this node current splits. Part goes to the load, part goes to the capacitor, and there are two loops here. Okay. But in this second stage here, the important is to understand that if the diode is conducting, okay, this voltage here is 0 if it is an ideal diode. So this asterisk voltage in the second stage is 0. Okay. Now the last variable, the inductor voltage. Okay. What happens in the first stage? So we are analyzing this voltage here. Okay. Of course, that in this first stage of operation, also there are also two loops, but different loops, because now current comes from the source. Okay, passes in the inductor. Again, there is a split. Part goes to the output, part goes through the capacitor, and then both comes here, and the loop closes to the source again. Okay. But if we look at this outer loop that we have here, okay, we can easily relate inductor voltage with input voltage and output voltage. Okay, if we look at this outer loop, we can say that VI is equal to VL plus VO, which is exactly this expression that we have here, since this is VL. Okay. But let's complete here the analysis of the voltage, and then we analyze the currents and we complete this expression. So in terms of the voltage, this relationship that I state, it means that I can say in a different way that VL is equal to VI minus VO. Okay, so it is the result that we have here. Okay, in the first stage, inductor voltage, this green waveform, is VI minus VO. Okay, and in the second stage, what do we have? Second stage, we have this. So we saw that the diode is conducting. This is inductor voltage. This is output voltage. And since this is a closed circuit, okay, VL is minus VO. Okay, and that's what we have here. VL is minus VO. This result for VL, so in this first stage, a positive value of inductor voltage, and in the second stage, a negative value. it indicates that in the first stage, inductor is absorbing energy from the source. And in the second stage, see we have a negative voltage, the inductor is releasing energy. Okay. So this is important, namely this result, because we are using this result to design the inductor and the capacitor. Okay, but for now we get this. In terms of the currents, so from this equation that I mentioned before, so VI is equal to VL plus VO. If I solve this equation in order to the current in the inductor, okay, because it is the unknown. Okay, I know what is my input voltage. I know what is the output voltage that I want. If I already design my inductor, okay, I can know how the current is variating. Okay, so if I solve this formula or this expression in order to the current, I get this result. Okay, and note that the variable time. So this is a constant. Variable time is here. So this term is the coefficient of t, but this coefficient is constant. L is constant, Vi is constant, and Vo we are assuming that it is constant. Okay, so this result shows us that the current variation is a linear variation. Okay, so that's why we get here that straight line. Okay, this straight line is as a result of this equation of the line. Okay. So this justifies how the current in the inductor is variating, but we have two more currents. Okay, so if we look at this node here, okay, we have the inductor current that enters the node, and then we have output current for the resistor and capacitor current. Okay. Now look, if the load is a resistor, as it is represented here, if we are assuming that the output voltage is constant, then by Ohm's law, output current is also constant. Okay, which means that, and noting that in this representation of the currents that we have here, zero is here. Okay, this is zero. So look at the capacitor current that has negative values and positive values. Okay, we know that when the current in the capacitor is negative, it is discharging, and when the values are positive, the capacitor is charging. Okay. And for the inductor, we know that when the current derivative is positive, so when the current is increasing, inductor is also charging. Okay, so note that the charge of the inductor does not correspond exactly to the same interval of the charge of the capacitor. Okay, the charge of the inductor occurs here, while the charge of the capacitor occurs here. Okay, but this is not very important in terms of the design that we are going to do. Okay. But finishing this analysis, so If the output voltage is constant, it means that the output current is constant. So it means that this inductor current that comes to this node, okay, we can say this way, that the DC component goes to the resistor and the AC component goes to the capacitor, okay, which is equivalent to say or to note that this capacitor current has that has no DC component. The average value is 0 of this current. Okay. And also from the nodes law, okay, you can say in a different way that from this inductor current, if we subtract the DC component, which is this constant IO, if we make this difference, okay, we get the capacitor current. Okay, so IL minus IO is equal to IC. Okay. Sorry. So more things. Well, here there is a small demonstration in order to check that even using the filter, okay, as I said before, this relationship is valid again. Okay, so output voltage is equal to D duty cycle times VI. Okay. So what we're going to see next is then how to design, how to select the values, the values that are interest for us for the inductor and for the capacitor. Okay, and so we are using this relationship or this result that I mentioned before. That was in the first stage of operation. We saw that the inductor voltage is equal to VI minus VO. Okay. So starting from that result, or using that result in the equation that relates inductor voltage and the current, this formula that you know, okay. I put the inductor in the first term, okay. What we have here is this, okay. And what we do next is then to say that in the first stage of operation, inductor voltage is equal to VI minus VO. Okay. And then what do we do next? We this is the derivative. Okay, we discretize this derivative. And if we look at this part of the current, so it is exactly the same graph. Okay, but I am identifying here the current variation between the minimum and the maximum. Okay, and this current variation that occurs also at the beginning, minimum to the maximum, is the same current variation. This variation occurs also in the first stage of operation. So I can discretize this derivative, okay, saying that DEL is the delta EL, current variation, okay, and this DT is this time interval from 0 to duty cycle times the period. Okay, so DT is equal to duty cycle times the period. Okay, so doing this, solving in order to the current variation. Okay, we get an expression that is important because we are going to use, and we can use in, well, essential two ways that I'm going to mention. Okay, and this is important because well, this expression relates the coordination with the inductor. So it is a way to design, to select a value for the inductor. One of the ways is to use this relationship. Okay, but I am going to first use a different approach. So typically in this kind of converters, it is interesting to work in the continuous conduction regime. In the last class, I mentioned this. We can have a continuous conduction regime or a discontinuous conduction regime. Okay. In a continuous conduction regime, it means that current is always positive. Okay. There is always current. And it is a desired mode of operation in the sense that it is the one where output voltage is D times Vi. So it is a very simple relationship that we try to use always. Okay. So it means that we must choose an inductor so that the current can be always positive. Okay. So that's the goal. So we can make here a mathematical analysis so that you can get an expression that enables us to design and choose the correct value. Okay. So the worst case is where we are in the border between the continuous and discontinuous regime, which is the same to say that this is zero current. Okay. So there is a current variation. Okay, current starts from 0, for instance. We get a maximum, and then it goes again to 0, and we have this kind of operation. Okay. So at the border, the worst case, minimum of the inductor current is 0. Okay. Then if we use this expression that we saw before, so note that we are analyzing inductor current. So we can use this formula, this result that I mentioned before. Remember this when I said that the current has a linear variation. Okay, so it is this current that we are using, and so we can say that of current is 0, and at this time instant, okay, we are at T on, at time equal to T on. Okay, and if we add here a second equation that says that this current variation, or in another way, that the average value is exactly at the middle of this current variation. Okay, then I am sure that I am in continuous conduction if this current variation is lower than twice of the average value. Okay. Imagine that this average value is 10 amps. Okay. If this current variation is 8 amps, okay, so 4 in the higher part, let's say, and another 4 in the lower part. I am in continuous conduction because the minimum is 4 10 minus 4, so 6, and the maximum 14. Okay. So as long as the delta L is lower than twice the average value, okay, I am always in continuous conduction. Okay, so if I use this condition together with the previous equation, and if I solve this in order to the variable L, I get this inequation that tells me what is the minimum value of the inductor that I must choose in order to guarantee that we are in continuous conduction. Okay. So given the parameters of the converter, the load, period, so the frequency, the duty cycle, okay, from these values that I know, I can design or choose a value for the inductor. Okay. This is one way. The second way, okay, and the value of the inductor that comes from this equation, okay, we call the critical inductance, because it is the minimum value that assures that we are in continuous conduction. Okay. Another typical way to make the design is to choose a value of the current variation as a fraction of the average value. Okay. So imagine again this situation here. Imagine again the average value of the current, the 10 amps. Okay. If I say that my current variation is 20% or 30% or 40% of the average value, okay, imagine that I say that the current variation is 20%. So I'm saying that this current is 2 amps. Okay. So it means that the minimum is 8, sorry, the minimum is 9, and the maximum is 11. So I'm in continuous conduction. Okay. So if I say that the current variation is a fraction, okay, of the average value of the current, it is another way that automatically guarantees that we are in continuous conduction. Okay. So by this second approach, I define a current variation. Okay, and how can I design my inductor? Well, this result. Okay, I specify a current variation, and I calculate the inductor. Okay, so this is very typical, and basically we can say, and using this second approach, that we can design the inductor from the current variation. And we are going to see that we are going to design the capacitor using the voltage variation. Okay? Because we are assuming, we start basically this class saying that the voltage is constant. Okay? So we are assuming that the variation is extremely slow. Okay, but if we choose a wrong capacitor, eventually we cannot guarantee that. Okay. So one way to be sure that we can guarantee that is to specify a value for the voltage variation. So imagine that we want here 20 volts. Okay. And suppose that our input is, I don't know, 100. Okay. And I want 20 at the output. And if I want the voltage to be practically constant, I can say that, okay, imagine well, exaggerating that my ripple, the voltage ripple, the voltage variation is 20 millivolt. Okay, so 1,000 lower. Okay, so this is my delta VO. And the idea is to, from this specification, to find what is the value of the capacitor so that this is true. Okay. So for that, I must have and use an expression that relates these two quantities. Okay, the voltage variation and the capacitor. And that's what you have here in this last slide. Using this relation between the voltage and the charge in a capacitor, okay? And since the charge in a capacitor is the current that flows along the time, okay? That is equivalent to an integral, and we can see the integral as an area that we can calculate. Okay. So again, from this picture of the currents, what we are doing here is to say that this quantity of charge corresponds to the area that it is represented here. Okay, and this is a triangle. So the calculation that we are doing is to calculate this charge, okay, as the area of this triangle. So using the base and the 8 of the triangle. So what we have here is the formula of the area of a triangle. Okay, the base times the 8 divided by 2. Okay. So from this result, and using the previous result of the current variation, okay, what we do is to replace here delta VL, and we simplify, and we get this relation. And since all the parameters are known, as well as the inductor, if we design from the previous approach, okay, then if we specify a voltage variation in an absolute way, as I did before, I said delta VO equal to 20 millivolt, okay? Or I can make a specification in a relative way. I can say that this fraction, so the voltage variation divided by the output voltage is 1%. Okay, the same way as we have done in the current. Okay, I can say delta VO is 1% or 2% or 5%. Okay, so I know from this specification, okay, I can calculate my capacitor. Okay, so this equation that I have here, well, this is an equation, but this capacitor is taken from here. Okay, but written in this form, it means that there is a minimum value of the capacitor that give me the desired variation that I want at the output. Okay. So in terms of analysis of this converter, we are done. This is the I think that I told in the last class. This is the converter that you are going to study and implement in the laboratory work number 3. Okay. So it is this circuit here. So in the laboratory class, you are going to build with components that we are giving to you at the class. You are going to build this converter. This is the converter that we have analyzed. Okay, and we are going to use here an extra component, which is a driver that I'm going to explain now in the following minutes. But this is, let's say, the power part that you are going to construct. Okay. This driver, this IC, makes the connection between the control part and the power part. Okay, so this is the power part. It is the converter. And the control signal, the pulse width modulation control signal comes from where? Well, we put here in this input of the driver, but this PWM signal, it is the one that you are going to build at home. Okay, so you are making the preparation in terms of the design and calculation of components, but I recall that you must build in the breadboard, okay, that control part and bring that circuit to the class in order to test if it is working. And if it is working, you get the signal from your circuit, you put here in this input of the driver, and we hope that the whole system works. Okay. But why are we using this driver? So I'm trying to explain this now. I'm going to use here some slides from the previous year that I'm going to update, and they are not still in Moodle, but it will be, okay? So the driver or the drivers can implement several functions, okay? This type of drivers we can use to control either MOSFETs and the IGBTs that we are going to analyze also, okay? I already mentioned in the last class that sometimes we need to have a dead time or a complementary signal, so drivers can provide these functionalities, as well as other functionalities as protection in terms of overcurrent, isolation between control part and power part. Okay, we can electrically isolate both circuits using this driver. We can also use drivers to adapt levels of voltage and current, okay, because I can have at the input of the driver a signal that can vary between, let's say, 0 and 5 volt, okay. But eventually, I need at the output, okay, to control my transistors. Eventually, I need higher values of voltage, for instance, plus 15, 0 plus 15, or also minus 15 to plus 15. Okay. So drivers make this conversion between an input signal to another input signal with different characteristics, okay, that sometimes are needed in order to the transistor to switch as we want, okay. It is mainly related to the frequencies. The higher the frequencies, typically the higher the voltage we need to use, okay. So this is related to this functionality, okay. And the last one, and it is the reason that we are using in this project, is the bootstrap circuit, okay. Why do we need this? Well, let's look here. Well, let me show again your circuit here. So you are using a MOSFET, okay, not the terminals gate, source, and drain, okay. As I said before, we must apply a control signal between the gate and the source, okay. But the problem is that the source terminal, it is not at the ground terminal, either of the power part and the control part. Okay, this is the 0. But if I want to apply, let's say, 10 volt as gate to source voltage, I don't have here my 0 reference. Okay, which means that I must work. And why? Because this node here, the voltage at this node is floating. Floating in the sense that it depends if, for instance, if this diode is conducting or not. Okay, if it is conducting or not, I will have different voltage here. So it means that the control signal that I apply between the gate and the source must be floating. Okay, in the sense that the potential in this node is variable. Okay, so that's why we have different kinds of drivers that we call low side drivers. Low side drivers. Okay, when the 0 of the power part is the same of the control part, we have high side drivers where the 0 of the control part is here, but the source of my transistor is not at the ground. Okay, ground is not here. And an equivalent situation is where we have both situations in a scheme like this, that it is very usual. We have two transistors connected this way. Okay, this is the ground of the power part. It is the same for the control part. Okay, but now we have here two transistors. This is gate source from the lower device, and this is gate source from the upper device. That's why you call this the high side part and the low side part. Okay, if I want to use gate source voltage equal to 10 volt, okay, here there is no problem. But again, this voltage that I apply here must be floating, because I don't have here 0 volt. 0 volt is down here. Okay, so I must use a mechanism so that this voltage here is floating, and that's what these half bridge drivers, as well as the high side drivers, provide. Okay, essentially using this extra diode and this extra capacitor, it provides this voltage to be floating. Okay, and in your project you are using exactly this driver, although we don't have two transistors. Okay, but we have a situation exactly where the source, okay, must be floating. So you can see this transistor as an high side transistor, and this diode is in the lower part of the converter. Okay, so it is a situation where, although we have only one transistor, we can use an half bridge driver to so that we are able to put here a signal this way, in a floating way. So for today we are done. So tomorrow I will put in Moodle the lab assignment of this work number 3 that some of you are going to build next week, and that's it.
Teacher, I have a question.
Mm-hmm.
This is the circuit that we will build in class, or is this the circuit that we have to bring from home?
No, this is the circuit that you are going to build at the laboratory, okay? And we are going to give you these components, okay? You must bring your control signal from home, and your control signal is the one that generates this pulse width modulation control signal.
Okay.
Okay?
Thank you.
More questions? Okay, so see you next time.